A very good morning and welcome back to this course of microwave engineering. So from today's lecture onwards, we will be starting with module number 5 or chapter number 5 in our prescribed syllabus. So from today, we will be starting with our fifth module, that is microwave measurements. In microwave measurements, we will investigate how to measure the different parameters of a microwave signal by means of a suitable technique, right? And we will distinguish here in this topic how the low frequency measurements are different from high frequency measurement or the microwave measurement, right? So the different types of parameters of a microwave signal, for example, a frequency, reflection coefficient, the transmission loss, the voltage standing wave ratio, right? So such a kind of the parameters of a microwave signal can be conveniently measured using a low cost laboratory technique. So in this particular module, we are going to investigate how to measure these parameters of a microwave signal in the laboratory. And based on it, we will establish a theoretical development. So let us start with module number 5, that is microwave measurements. So I will start from here. I will give the title as microwave measurements. Now first of all, you should know the basic difference between the microwave measurement technique and low frequency measurement technique. Okay, so measurement techniques I will classify into two categories broadly. First is a low frequency measurement. And second is high frequency measurement, or that is nothing but our microwave measurement. We can call it as a microwave measurement, high frequency measurement, because we already know that microwaves are operating at a higher frequency. That's why the microwaves are being classified into high frequency measurements. So if you consider the low frequency measurement, okay, so a signal which is having lower frequency, and if you want to measure that signal into various types of a parameter, okay, so normally in low frequency signal the measurement is restricted up to certain circuit parameters. Okay, so here the specialty of low frequency measurement is the measurement is limited to circuit parameters, right? And we already know how the circuit parameters are described. The circuit parameters are voltage, right, current, power, frequency. All these are the parameters. So here I would like to highlight these as the parameters of measurements at low frequency. So in order to measure or in order to quantify the signal by means of a suitable parameter, voltage, current, power, frequency, these are the parameters with which a low frequency signal can be computed or it can be estimated, right? On the similar basis, if we consider the high frequency measurement, there is a slight difference in the measurement procedure. So here measurement is governed by wave nature. Okay, so for example, if we take a transmission line over here, right? So this transmission line is supplied with some generator voltage Vg. Now this generator voltage will set up a current over this transmission line. Let us say it is a Ig. Okay, so unless and until this transmission line over here, this is a transmission line. If this transmission line is not lossless, then please remember at that time the voltages over the transmission line, okay, so those are going to be different. Okay, so when we feed a voltage across a transmission line, and if the transmission line is not lossless, it is a lossy transmission line, then at that time the voltage as well as the current over the length of the transmission line is going to vary, right? So that means measurement of the signal over the transmission line is dependent on voltages and currents. Okay, on the other hand, if this transmission line is lossless, at that time the voltage and current are supposed to be uniform over the transmission line, and at that time we should able to analyze this transmission in terms of a power rather than in terms of a voltage and current, because voltage and current are supposed to getting fluctuated over the length of the transmission line, as they are dependent upon the length of the transmission line, right? So here the parameters like voltage and current are combinedly measured in terms of a power, and the other parameters at high frequency that we are interested in, like voltage standing wave ratio, impedance, right, reflection coefficient, and so on, right? So at high frequency, normally we will characterize a signal in terms of power, in terms of VSWR, in terms of impedance, and in terms of reflection coefficient. And voltage and current, these are the parameters which are used to measure the signal at a low frequency, because we know that at low frequency everything is lumped element, right? So in that particular case, at low frequency, the values of the parameter are not going to with the length of the material. But on the other hand, during the high frequency operation, the voltages and current are going to vary over the given transmission line, provided if it is a non-lossless transmission line. Okay, on the other hand, if you consider that the transmission line is lossless, then the voltages and current over the transmission line are supposed to be uniform, right? So that's why, as the voltage, we cannot make a transmission line completely lossless. So that means the voltage and current are going to continuously fluctuate over the transmission line. So at that time, instead of calculating the transmission line parameters into voltages and currents, what we do is, instead of that, we will measure the power. So this is the choice whenever we want to quantify the circuit parameter being operated at a higher frequency, right? So how the microwave measurements are carried out, right? So the second particularly problem associated with high frequency measurement is that, so in order to measure the high frequency parameter directly, whatever instrument that we are going to make use of, okay, so here I will write it down, the drawback of direct measurement. So here I will write limitation of direct high frequency measurement. So the limitation of direct high frequency measurement is that why we cannot make use of direct high frequency measurement is that the instruments, okay, so the instruments or the devices instruments, or you can call it as a test equipments. Okay, so instruments and test equipments which can measure the microwave parameters at a high frequency. So the example of these type of instruments are vector network analyzer, in short we call it as a VNA. Then we can make use of a spectrum analyzer, okay, and we can also directly make use of a power meters. Okay, so please remember, all these instruments and test equipments are very expensive, but the feature that they are going to offer to us is that we can make use of these devices directly in order to measure the parameters of the microwave. But on the other hand, these devices are very expensive and they are costly. Therefore, the direct high frequency measurement is limited to be an cost effective solution. Okay, so it is not a cost effective solution in order to make use of these highly expensive instrument in order to measure the microwave properties. So there is another technique in which we are going to make use of low cost, inexpensive, laboratory based standard measurement system. So what we do in that particular case, in that standard technique in the laboratory, we are going to make use of a modulating signal, which is normally we take 1 kilohertz square wave, and this square wave is used to modulate the microwave signal. Okay, so directly measurement of high frequency requires the use of sophisticated equipments like vector network analyzer, spectrum analyzer, and power meter, right? And these instruments are very costly and expensive, but they are able to measure the frequency and the other properties of the microwave directly. On the other hand, if we want to look for a cost effective method in order to measure the properties of the microwave, so what we do in the laboratory is, this is a low cost option. In the laboratory, we will make use of 1 kilohertz square wave as a modulating signal, and the properties of the microwave are getting measured by measuring the modulating signal after the demodulation process. So that procedure we will see. And normally in the measurement at the laboratory, instead of using the direct high-end equipment in order to measure the properties of the microwave, we normally employ this second method, which is a cost-effective solution, in which we are going to make use of certain modulating signal, and that modulating signal is normally 1 kilohertz square wave we are going to utilize. So this is just the introduction of the microwave measurement, how the microwave measurements are different from low frequency measurement, what are the limitations and benefits associated with these different types of measurement, right? And what are the different ways in which the parameters at high frequency can be measured. So that is by using a direct frequency method, using expensive equipments, and the other method is the laboratory standard method, which will provide us a cost effective solution. So with this introduction of microwave measurement, let us start with measurement of the first parameter related to the microwave. And the first parameter that we are going to see theoretically a procedure, that is the measurement of voltage standing wave ratio. Measurement of voltage standing wave ratio. So we will start with this first parameter. I will write over here, measurement of voltage standing wave ratio. Or in short, we call it as a VSWR. Now, first of all, we should know the meaning of what is VSWR. Okay, so the VSWR is measure of impedance matching. Okay, so what is the VSWR? What is the interpretation of VSWR? Why we want to measure the VSWR? The VSWR is a measure of impedance for a given device, or circuit or a transmission line. Okay, so VSWR is one of the parameter which is used to measure at high frequency operation, right? So VSWR is just a measure of impedance matching capability of a particular given device or circuit or even the transmission line. Okay, so a simple requirement of VSWR, why we want to measure a VSWR? The VSWR is an indicative measure of how well a particular given device, circuit, equipment or transmission line is capable of impedance matching. So this property is very important and we want to know what is the VSWR value of the given circuit, equipment or even of the transmission line. By knowing the VSWR, we can interpret the behavior of impedance matching of that particular device. Okay, so here in this particular session, we will develop a theory in which we will establish a stepwise procedure to measure the VSWR of the high frequency signal, right? So here the voltage standing wave ratio is also known as a standing wave ratio. Okay, and this voltage standing wave ratio is related with a reflection coefficient. Okay, so a simple relationship between the voltage standing wave ratio and the reflection coefficient is given by, we know that VSWR, or in other words it is also given as standing wave ratio, or sometimes it is also written as only S. So this standing wave ratio is measured for the given device by taking a ratio of maximum voltage to the minimum voltage. Or the same equation of a standing wave ratio in terms of reflection coefficient is given by 1 plus mod gamma divided by 1 minus mod gamma. Okay, so where S stands for standing wave ratio, right, and gamma stands for reflection coefficient. The same equation of VSWR can be rewritten in terms of reflection coefficient gamma as S minus 1 upon S plus 1. Okay, so from this we can establish a relationship when the standing wave ratio is equal to 1. When standing wave ratio becomes 1, the reflection will become 0, right? When the reflection becomes 0, that indicates no reflected wave, right? No reflected wave, and hence matching is achieved. Matching means impedance matching is achieved. On the other hand, if the standing wave ratio is greater than 1, okay, or it is any value which is greater than 1, in that particular case, if I write S is greater than 1, then at that time the reflection coefficient will become non-zero, right? So this indicates wave reflection, right? And if the wave is reflected, this indicates mismatch. This indicates mismatch. I'll write it again. Right? So this is a simple theory. By knowing the standing wave ratio of a particular device, circuit or transmission line, we can interpret its behavior for impedance matching. If the standing wave ratio becomes 1, reflection coefficient becomes 0, and that indicate a good matching is achieved. On the other hand, if the standing wave ratio is greater than 1, in that particular case, the reflection coefficient will become non-zero. That indicate that certain wave is getting reflected back. And if the wave is getting reflected back in the operation, it indicates that there is a mismatch and the impedance matching is not perfect. So here we will develop a theory how to measure the voltage standing wave ratio. Once you know the voltage standing wave ratio, we can calculate the reflection coefficient, that is gamma, and by knowing the value of gamma, we can interpret whether the matching of transmission line or that particular circuit or that particular device is good or it is bad, right? So here there are two different mechanisms of measurement of voltage standing wave ratio. So there are two different theory. Okay, so first there are two techniques. So I will write there are two techniques to measure VSWR. Okay, so in first technique we will measure low values of VSWR. So in first technique we measure low values of VSWR, and in second technique we will measure high values of VSWR. High values of VSWR. Okay, so can you imagine what should be the maximum value of standing wave ratio? The minimum value of standing wave ratio from this particular relationship, minimum value of standing wave ratio is equal to 1, and maximum value of standing wave ratio is equal to infinite. Okay, so we are going to divide the procedure into two parts. First procedure we will see how to measure the low values of voltage standing wave ratio. Okay, so low values of voltage standing wave ratio, that means standing wave ratio obtained less than 20. Okay, and there is another technique which we call high values of voltage standing wave ratio, and the values of a standing wave ratio greater than 20 are normally termed as high values of voltage standing wave ratio. So there are two separate techniques to measure the voltage standing wave ratio. Now let us first see the method of low values of VSWR measurement. So first of all, let us see low VSWR measurement, low values of VSWR measurement. Okay, so how to measure the low values of VSWR measurement which are up to values 20. Now for that, as we already said, we are going to take help of low cost laboratory measurement. Now in this laboratory measurement we have a set of microwave source. Okay, and this microwave source is getting modulated with a certain signal. Okay, and this type of procedure we will set up for measurement of low values of VSWR. So I will draw a block diagram which will illustrate you a measurement procedure of low values of voltage standing wave ratio. Okay, this technique or this procedure is totally laboratory based, and it will not involve the use of highly expensive equipments like network analyzer and all those things. Only the thing that we should have is a source of microwave and a modulating signal and a low cost time domain output device. For an example, a cathode ray oscilloscope or digital storage oscilloscope. Okay, so I will draw a block diagram of low values of VSWR measurement. Okay, so here I will come, I will start drawing over here. So here a first block, then we this first block is a microwave source. This first block is a microwave source. I will write here microwave source. Okay, then we have a second block. The second block is the isolator. The isolator we saw in the case of waveguide. What is its job? The job of the isolator is to stop the reverse gating signal. Isolator. Okay, and we have a third block, frequency meter. I will write here as a frequency meter. So this is a frequency meter or wave meter. We already know how to make use of this frequency wave meter, and there afterwards we have a variable attenuator. So here we have a variable attenuator. Okay, so this variable attenuator is connected to slotted transmission line section. So here it is a slotted line or a transmission line. It is a slotted section through which we can move our tunable probe. So above which we will place our tunable probe or tune probe, through which we can take out the signal. Okay, and the VSWR of a particular device. Okay, so we are going to measure VSWR of certain device or certain equipment or even a transmission line, right? So that device under test we are going to place over here. So this DUT is nothing but the device whose VSWR we are going to measure. And finally over here we have a matched load. So here we have a matched load. Okay, now this tunable probe is connected at the output device. Now this device is either a CRO or VSWR meter. Okay, and all these equipments will be connected together. So a microwave source is connected to the isolator. Isolator is connected to the frequency meter. Then from frequency meter it is a variable attenuator, and from variable attenuator it will go to the slotted waveguide section, through which we are going to measure the voltage standing wave ratio of this device under test. Okay, so this device under test, it could be any particular device whose VSWR we want to measure. So this device under test, it could be any equipment, okay, or it could be a circuit, or it could be a transmission line even, whose VSWR we want to measure. Okay, and this device is connected with a matched load at the output, so that reflection will not take place from here. Now the slotted transmission line is connected with a tunable probe, and the tunable probe will act as a output device, and it is connected to the output device like CRO or VSWR meter. So this is a typical setup of the measurement procedure of small values of voltage standing wave ratio, right? So here, what is the procedure to measure the voltage standing wave ratio? So the voltage standing wave ratio is measured with the help of this block diagram. Now here, first of all, we need to make certain adjustment. The variable attenuator, the frequency meter, and the microwave source. So here in the microwave source, please remember, we have not shown any modulating signal, but it is assumed that the microwave source is generating the microwave signal as well as the modulating signal. So here what we can do is we can show separately a modulating source. So here I will draw it. Here I will draw. So this is usually 1 kilohertz square wave signal. Okay, so this 1 kilohertz square wave signal is modulated with the microwave source. Okay, and this combined signal will be passed over the isolator. The isolator will take care that the signal which is forwarded into the forward direction will not get reverted, and in between we are going to place the frequency meter in order to observe the frequency of operation. The variable attenuator is used to attenuate the signal, and this signal is passed over to the device under test whose VSWR we want to measure via slotted line. Okay, and this device under test whose VSWR we want to measure is terminated at the other side with the match load, right? So here how we are going to measure the VSWR, right? So what we do is the probe or the slotted line we are going to move along the non-radiating slot from the load until a peak value of VSWR is observed on the VSWR meter. Okay, so what we do is when we make this type of a connection diagram, right, what we are going to do is we are going to move the probe carriage of a tunable probe over this slotted line section from the load towards generator. Okay, and we want to read maximum value at the CRO or at the VSWR meter. We can either connect CRO or we can make use of the VSWR meter. Okay, so what we do is I will write over here. After this particular arrangement, what we do is we move probe position from load towards source in order to get maximum voltage on CRO, or instead of making CRO, if we are making use of a VSWR meter, maximum reading of VSWR or maximum reading or we can also call it as a maximum deflection by VSWR meter. Please remember, you either connect a CRO or a voltage standing wave ratio meter at the output. If we are making use of a CRO, observe the maximum value of the voltage. On the other hand, if we are using a VSWR meter, see to it that it is showing the maximum deflection and adjust the position of the probe over the slotted section. Okay, so what we will get in this particular procedure, now in doing so we will measure Vmax. Vmax is measured. Okay, so what we do then, we will move again on the left hand side adjacent. Okay, so once we get Vmax point, we move towards generator to find minimum voltage position. Okay, so minimum voltage position when you arrive by moving the tunable probe over the slotted waveguide section, at that time V minimum is measured by the CRO. So on the CRO you will get minimum voltage. V minimum is measured on the CRO, or instead of using a CRO, if you are use of a VSWR meter, the VSWR meter will show minimum deflection. Okay, so V minimum and V maximum is measured. So what you can measure then? So directly VSWR in that particular case is simply given by V max divided by V min. Okay, so you know what is the value of V max, you know what is the value of V minimum. You can take the ratio and you will find the value of a VSWR. The value of the VSWR measured by this particular technique varies between 0 to 20, less than or equal to 20. And this particular measurement procedure is totally accepted for the standing wave ratio measurement up to 20, right? So if the standing wave ratio is greater than 20, then this particular measurement procedure is not suitable. Now in that particular case, we are going to make use of the second method, that is here the second method we call it as a high values of VSWR measurement So the second method is, what if the value of the VSWR is greater than 20, then this particular method we are not going to make use of. So at that time we will switch to some other technique at where the standing wave ratios are greater than 20. Okay, so this operation is similar to earlier operation, only some additional procedure we are going to make. Okay, so high values of VSWR measurement. So the high value of the VSWR, the power at the voltage maximum and voltage minimum is large, and it is very difficult that this voltage is going to remain at the detector square law region. Okay, because the diode current of the detector is going to exceed in the excessive of 20 microampere. So at that time, if the voltages are produced so high, then the detector cannot measure the produced voltages, right? So at that particular time we are going to make use of this second method, and this second method of VSWR measurement is sometimes also known as double minima method. So this second method of VSWR measurement, at which we are going to measure the high values of the VSWR, is also known as double minima method. Now what is this double minima method? See over here, I will first draw a diagram and then I will explain. On the x-axis, let us say x is a indicating of a distance where we get the minimum or maximum voltage when we travel along the slotted section, and the voltage obtained along the x direction that we are going to plot on vertical axis, right? So what we are going to do is, the voltage minimum, let us say this is the position, okay, at which voltage minimum is observed over the slotted waveguide section, and this voltage minimum is observed at a certain distance x minimum. Okay, so what is the procedure over here is, say we are going to make use of the same setup. What we do is, we are going to make movement of the probe using the slotted waveguide section from the load to source. Okay, so we move the tube probe position on the slotted waveguide section from the match load towards the generator, and first of all we will find the position of minimum voltage. Okay, so the position of minimum voltage is indicated by x min, because on the slotted waveguide section, please remember, there is a direct scale of the marking of the distance. So x min stands for distance of voltage minima, Okay, so what we are going to do is, when we get the voltage minimum, Okay, we are going to note down the deflection on the VSWR meter, right? So here what we are going to do is the VSWR is measured slightly in a different way. Now in this particular case, the VSWR is measured by evaluating the formula VSWR. In this particular case, it is given by the guide wavelength lambda g divided by pi multiplied by delta x. Okay, so where delta x is the difference of distance, and this difference of distance is x2 minus x1. Okay, now what is x2 and x1? x2 and x1 are the position of the 3 dB down point of the voltage minima. Okay, so suppose here the V minima is obtained at this particular position. Okay, so in this way, you will get a curve like this. Okay, so at this position you will get a minimum voltage. Okay, so a 3 dB down point you need to find out. Above and below that minimum distance, so the distance at which we will get 3 dB down value of that voltage minima, we call it as a x1 and x2. Okay, so this difference of voltage minima is 3 dB down. Okay, so this V minimum is 3 dB down, and this is the actual minimum voltage which we obtain at x min. Okay, so at x minimum distance, the voltage we get is a V minimum. Okay, so 3 dB down to this value we need to find out. So what we do is we will slightly move the probe position on the left hand side. Okay, the left hand side is indicated by this deviation from x min to x1, x minimum to x1. This distance will give 3 dB line, 3 dB point. So this 3 dB point is over here. Okay, and similarly when I move on the right hand side from the x min, again the V minimum will change by 3 dB. So from x min to x2 I will get another 3 dB point. So please remember, what is the 3 dB point? 3 dB point is the voltage fluctuation of minimum voltage to its value 3 dB upper or lower. So this value is a 3 dB upper value of voltage minimum, and this value is 3 dB lower value. So what we do is we will move the probe position on the slotted waveguide section around the minimum distance x min, such that I will get 2 points at 3 dB. Okay, so these 2 points at which the minimum voltage drops or increases by 3 dB, those distances I will note down, and these distances are given by x1 and x2. Okay, so we measure this x1 and x2 and we will take the difference. I will get a delta x. Okay, and what is a lambda g? Lambda g is the guide wavelength. Okay, so lambda g is guide wavelength. So how to measure guide wavelength? So I will give the procedure. So we know how to measure x1 and x2. So lambda g is a guide wavelength. Okay, so in order to measure the guide wavelength, so how we can move, say the position of the slotted waveguide section is arranged such that whenever we measure the distance between two minima, it is equal to half of the guide wavelength. Okay, so what we do is, in order to measure the guide wavelength, we will find out two voltage minima position. Okay, so let us say D is distance between two voltage minimas. two voltage minima. Then this distance corresponds to the guide wavelength divided by 2. So you measure the distance between two minima so that you will get this small d. Once you know the small d, you multiply it by 2, you will get the guide wavelength. So you know the guide wavelength, you know the difference of the distance of 3 dB point of that minimum voltage. You put these values over here and find out the value of VSWR. Now in this particular case, the value of a VSWR you are going to get greater than 20 and less than or equal to infinity. Okay, so this is the second technique which makes use of the same setup in order to measure the high values of VSWR. And sometimes this particular method of measurement of a VSWR is known as double minima method. Okay, so what we did, that I will elaborate you in a brief by drawing a particular diagram now. Okay, so I will choose a different color. See, whenever a voltage standing wave ratio is formed, let us say this is a generator side, or rather I will draw in a different way. And say this is a load side. This is a load side and generator side. Okay, suppose if there is a mismatch from the load side, so if the mismatch happens, a standing wave ratio is formed from the load side in this way. Okay, over the transmission line or in the particular device. Okay, and this will continue. So what is this? This we call it as a voltage standing wave ratio. This voltage standing wave ratio is formed by mixing the forward traveling wave, right? The forward traveling wave is taking place from the generator, and reverse traveling wave will take place from the mismatched load. This is the reverse wave. So when these two waves interfere with each other, we will get such a kind of a VSWR pattern over the transmission line or in the device or in the circuit. Okay, so how to measure the minimum voltage? Here we are going to put the probe at the load side. So here we are going to place that tunable probe, right? And this tunable probe, what we are going to do is we are going to move towards generator in this way, towards generator, right, in this way. I am telling you the actual procedure how we are doing in a practical. And this tunable probe is connected to either a CRO or a VSWR meter. Okay, so when we move, first we will get V maximum, okay, and then we will get V minimum. So this is the V minimum. At V minimum, we will note down what is the distance. Let us say this is a x1. Then when we go on the left hand side further, we will get again V maximum over here, right, at this particular point. And when we continue going further, I will get second V minimum. So let us call this a second V minimum. This is first V minimum. And the second V minimum, the distance at which we get is say x2. Okay, so we got x1 and we got x2. So x1 is distance of first minima, right, and x2 is distance of second minima. So if you take the absolute difference of x1 to x2, this difference of between the two successive minima of the voltage standing wave ratio pattern is equal to guide wavelength divided by 2. And from this you can find out what is the value of lambda g. Once you know the value of lambda g, you can put this value of lambda g in the numerator. Okay, and what is the procedure to measure this delta x? So the delta x, it relates with minimum voltage. So here what you do is, first of all, you bring the position of the tunable probe at the first voltage minima. Now this x1 will become x min, right? So this x min is over here, right? So this is that x min. You bring the tunable probe position where you will find the first minima, and what you do is you will go on the left hand side of this x minima and find out that the voltage or the deflection is 3 dB above. So when you go on the left hand side from this x minimum, it will go 3 dB above. Okay, so this 3 dB above, at which you will find that is the increase, so you note down what is the x2. So when you get 3 dB above, the corresponding distance of this tunable probe is x2, right? So similarly, you again bring the tunable probe at x minimum, okay, and then again go on the right hand side. Now when you go on the right hand side, you will get minus 3 dB below, and the voltage or the deflection will drop, and this corresponding position is say x1. Okay, this is say x1, so over here. Okay, so you know what is the value of x2, you know what is the value of x1, these are the distances. Okay, so here you can evaluate delta x is equal to absolute of x1 minus x2. So you know the delta x. Now this value of the delta x you put over here, multiplied by pi, okay, and divide the guide wavelength by the product of pi and delta x, and then you will get directly VSWR. Okay, so this is how a simple procedure to measure voltage standing wave ratio of a particular device, provided that device is operating at a high frequency or it is operating at microwave signal. So here in the block diagram of VSWR measurement, please remember this device under test, it could be an equipment, or it could be representing a circuit, or even it could be representing a plain transmission line whose voltage standing wave ratio we want to determine. And please remember, voltage standing wave ratio is one of the microwave parameter of the given device, equipment, or the transmission line. Okay, so I hope you understood the two different mechanism. These are the same mechanism and these are going to make use of the same setup. Only the method is different, that in the case of low values of VSWR measurement, what we are going to do is we are going to directly measure the position where we will get maximum voltage and where we will get minimum voltage, and by taking the simple ratio in this way we can measure the value of VSWR. In that particular case, we assume that the VSWR is less than or equal to 20. On the other hand, if we want to measure the VSWR which is greater than 20, at that time this method will not work, because the generated voltage, maximum voltage and minimum voltage, will not be in the range of the capacity by which the tunable probe operates, right? So at that time we will be making use of this double minima method. Okay, and this double minima method is also known as a technique in which high values of VSWR which are in excess of 20 can be measured. Okay, so the same is explained to you with the help of this wave diagram, right? I hope you understood the VSWR measurement technique for any particular given circuit, equipment, or any given transmission line. Thank you very much.